Appreciate the opportunity to be here and just kind of excited to talk about this topic because this is one of those areas where there was a kind of a pivotal time where I'm like, oh, I need to think more deeply about this. And what prompted that thinking more deeply is I was invited to speak at the Unbelievable conference over in the United Kingdom. Justin Brierley has this podcast that he does, and he hosts a conference. At the time, it was every year, and I got to share the stage with Bill Craig talking about whether the universe had a beginning or not, and spent some time fleshing out why I thought there was a beginning, pointing to some of the evidence towards that. And during the Q&A time, fellow raised his hand out in the audience, and he goes, and I don't remember the exact flavor of his question. I remember more our conversation afterwards, but he basically said, you know, there's this kind of quantum gravity model that says there's no beginning to the universe. What do you do with that? And I didn't quite get his question, so we interacted a little bit and went to a number of other questions. And then after my talk was over, I was kind of just milling around. People were talking with me, and he kind of waited for everybody. And he came up and he started talking to me. And I had a little chance to probe and ask more questions. And finally, what I realized this fellow was asking is like, you know, hey, we've got all this stuff that we're going out there. But when you look at these quantum gravity models don't have a beginning, and I can give you 3 or 4 of them that don't. So what are you going to do with that? And that was the genesis of this talk, because I realized he was asking a very important question. And one, it wasn't just trying to obscure or getting around, it had profound implications. And I'll kind of explain why those implications are so profound and how I've come to think about it afterwards. And hopefully you will find this helpful in how to think about it, because even in the midst of not having a final answer of whether the universe has a beginning, what I have discovered is that for all the ways throughout the last 120, 130 years that scientists have tried to get away from a beginning, the universe seems to keep pushing us back towards a beginning. So I just kind of want to highlight why that is and kind of give you a little bit of background so that hopefully you can be more equipped and more confident to trust that what the scriptures say about the beginning of the universe is actually an accurate description of the way our universe is. And so let's start with, did the universe begin? And let's kind of go explore why we think it did. And to give why we even ask this question, if you go back to the start of the 1900s, the scientific picture of the universe was really quite different than it is today. The universe was static and eternal and unchanging. And there are reasons for that go back into antiquity, go back even to how Newton envisioned gravity. But the universe was static and unchanging on the larger scale. Space and time just simply existed. They were eternal. That was just the way things were. And you had this weird phenomena, which was a little bit of a subtle phenomena, that as you moved through the universe, the laws of physics actually looked different. And it's related to how Maxwell saw the laws of physics and how Newton saw the laws of physics, and how those change as you move through the universe. And it's a very subtle point, except that it's such a subtle point that Einstein, when he was looking at this, recognized this and said, wait a second, I don't like that. And so what he did was actually said, what would it take to develop a theory where wherever you are in the universe, however you're moving, everybody sees the exact same laws of physics? And so it basically says you can't tell where you are based on looking at how the laws of physics looks, because everybody's going to see the exact same laws of physics. Or another way to state it is that the laws of physics don't depend on your motion or your location. And that seems like kind of a simple thing from a Christian. It's like, yeah, that's kind of exactly what I would expect in the universe. The universe is ultimately anchored in God's creative activity. It's ultimately anchored in his character. God is unchanging, so we would expect to see the way the universe behaves, his upholding of creation to be very reliable, and that's why we can talk about these things called laws of physics, ultimately anchored in his character. And Einstein basically codified that into our physical theory of how the universe behaves. And I can tell you this, every experimental test we've thrown at the theory of general relativity has passed with flying colors. Now, as Einstein developed his theory, what he recognized was that the solutions to this theory talked about a dynamic universe. Either the universe was expanding or it was contracting. And we can talk about the cosmological constant he introduced to get a static universe. All that really does point out is how prevalent the idea was that the universe was static. And it wasn't till about 15 years where that was just kind of abandoned, and we realized that was not the way to look at it. And one of the things I want to point out here, and why this fellow's comments to me about the quantum gravity were so important, is that when Einstein introduced his theory of general relativity, before that, space and time were just this fundamental entity that things happened within. But when Einstein introduced his theory of general relativity, it changed the way we thought about space and time. Space and time were now these dynamic quantities that could begin and end. That just wasn't even an option before general relativity triggered the way we think about it. And what this fellow was talking about, quantum gravity, has that same level of maybe we're just thinking about space and time wrong. And so that's why this fellow's comments to me made me go back and make sure to reevaluate and think about this more deeply. Because just as general relativity came in and said, all right, we can talk about a beginning to the universe, that's what the universe seems to be pointing us to. And so let's talk about whether there's a beginning or not. Well, about 15 years later, Einstein did introduce this cosmological constant so that things were static and unchanging. Well, Edwin Hubble, as he was using most powerful telescope at the time, was looking out, and what he found was that the more distant a galaxy was, the faster it moves away from us. And believe it or not, the faster it moves away is the easier measurement to make. But he was able to quantify how far away things were, at least in some rough sense. And he made this plot and showed that the farther away a galaxy was, the faster it was moving away from us. And you had this nice, it's kind of a blob on his plot, but we've since measured it, and it's this nice, very good linear relationship where we can see that, yes, the farther a galaxy away is, the faster it's moving away from us. And that's a telltale signature of an expanding universe. And so this validated Einstein's theories that said that the universe ought to be dynamic. And since it's expanding, the natural question to ask is if it's expanding, we can ask how long is that going to happen into the future, but the more interesting question is, did that always happen in the past? And so this was kind of the picture of the universe that people have, and I'm going to show this image and right away tell you that I hate it because it's an entirely inaccurate way of looking at things. But this is the way most people, this is kind of the image you have, is that you've got this stuff that starts in this thing and it expands out and makes this nice spherical shell. And it's just not the way we look at it because it's not an accurate picture of the universe. And I'll kind of give you one that I think is a little bit more accurate, but it's really hard to get a good, accurate picture of what the universe looks like from the outside when you're on the inside. But all that to say is that when Einstein developed his theory of relativity, revolutionary way of looking at things, revolutionary discovery by Hubble that the universe is expanding, kind of points towards a beginning. And kind of move up now up into the 1960s, and people are asking the question, does this really mean that there's a beginning or not? And this is where Stephen Hawking and Roger Penrose come into the equation. As they're sitting around talking about this, what they realize is that you can take Einstein's theory of general relativity, and when you talk about a black hole, you end up with this kind of scenario where let's take a clump of matter, and you've got all of this matter, and we're going to put it inside a horizon, and we say, all right, what happens as you move that forward in time? What ultimately happens under general relativity is that these trajectories of all of these particles cross. And why that's important is that where they cross, you get infinities where there's a boundary, or the laws of physics break down and there's a boundary to space and time. We can no longer talk about it. You can't, there's just a boundary. You can't go beyond that. And so inside a black hole, you get this. What Hawking and Penrose were able to do is say, let's apply that to the universe looking backwards in time. And you get the exact same phenomenon. This is where the Hawking-Penrose theorems come out of. And what you get is that as you run time backwards in our universe, eventually you run into this singularity where the laws of physics break down, and that's a reasonable descriptor of a beginning to the universe. And so this is why we think the universe, at least if you go back 50 years ago, why we think the universe might have a beginning. why it might not. Let's go look at that for a second. So, a little bit of audience participation here. Who knows what this is? Back in the back, yes. It's the moon, exactly. What's interesting about the moon in a number of different ways is that the moon is actually 1 second away from us. So it takes light about 1 second to get from the moon to us. It's a little bit more than that. It's like 200 to 220,000 miles. Light travels at about 186,000 miles per second, so it's a little bit further away. But what that means is that when you're outside looking at the moon, you don't see the moon as it is right now. You see the moon as it appeared 1 second ago. Now, on astronomy scales, that's largely irrelevant, especially when we're dealing with optical light for most people. But let's just kind of put that in the side and say, all right, well, we're seeing the sun as it looked 1 second ago. Who knows what this one is? Andromeda, yes, it's the Andromeda galaxy. And again, light has a travel time. This object is about 2.5 million light years away, which means that as we're looking at this object, we don't see it as it looks today. We see it as it looked 2.5 million years ago. Let's go out a little further. Who knows what this? That's not an object. Who knows what this is a picture of? The Hubble Deep Field. Entirely unrelated to this talk. How many stars are in this image? Now, I give you a multiple choice. Is it 5? Is it 500? Or is it 5,000? So let's have everybody. Who goes for 5? Got a taker, a couple takers. Who goes for 500? 5,000. It's 5. Let me find. Why can't I find them? Oh, there's one right there. You can see the little crosshatch pattern on it. There's one right there. There's a little crosshatch. I know there's one out around the edge. There's a crosshatch. There's about 5 of them in there. There's actually 10,000 objects in there, all of which are galaxies, which have millions and billions and trillions of stars in them. So, trick question, I know, but. So a lot of the galaxies we're seeing in this image, we're seeing we're seeing the light that has traveled from them for 5, 8, 10, 12 billion years. So again, we're looking back in time. We're seeing things as they were longer and longer ago, and eventually we get back to this. Who knows what this is? Sky map. That's the sky map of what? Cosmic microwave background radiation, exactly. One of the most distant things, unless we figure out how to see things with neutrinos, maybe gravitational waves will get beyond this, but this is one of the most ancient pictures we're ever going to get of the universe. And again, we're seeing this. This is a picture of the universe as it appeared almost 14 billion years ago. And so as we try and look farther and farther and farther and farther away, we look further and further and further and further back in time. And what that means is that because the universe that we know has only been around for about 14 billion years, speed of light is finite, that means there's a limit to how far out we can see. And so this actually changes our picture of how we think about the universe. And instead of the universe starting as this spherical blob that expands out, it's just there. And it grows over time. And if we kind of mark out the distance between two things and let it grow for a while, what we can see, and this kind of illustrates what Hubble found, is that this was closer together and it moved apart some. This one was further apart and it moved apart more. So the further away things are, the faster they're moving away. And it just continues to expand. I stopped it there. The universe doesn't actually pause, but it continues to expand and grow, and you can draw on there an observable universe. But given the way we think about our universe, there's almost certainly far more stuff out there beyond what we can see. And so this brings the idea of a multiverse into play. And our best explanation for our best cosmological model for where we are today is not Big Bang cosmology, it's inflationary Big Bang cosmology. And the way inflation works is that there's this stuff that rapidly expands, and it takes stuff that was in causal contact and can move it outside causal contact, because while the speed of light is a limit on how fast you can move through space, it is not a limit on how fast space can expand. And so if inflation happened, our universe is far larger than what we can see. But as people investigate how inflation works, what they realize is that not only may there be more stuff beyond what we can see, it can actually be more intriguing than that. So the picture we have is we've got this observable universe, which is defined as the most distant region of the universe where light can propagate to Earth within the age of the universe. And of necessity, it's centered on our observable universe, or centered on Earth. Doesn't mean Earth's special. If you go to the Andromeda Galaxy, you'd do the same calculation and you'd have an observable universe centered on the Andromeda Galaxy. But it's just a reflection that there's a limit to how far out we can see. And so the question is, what else is out there? I mean, there's obviously almost certainly going to be more stuff out there. But as we look at, not only did inflation happen, that says there's more stuff out there, but our models of how inflation works say not only is there more stuff out there, there's other realms of space that are entirely outside of our ability to see. And the fascinating part about how this multiverse works, or how this inflation works, is it's not universe begins, it inflates, stops inflating, and continues on. The science pretty convincingly shows you can't get that model to work because inflation, once it starts in that manner, it doesn't ever end in a way that produces a universe that looks like ours. It ends up way too clumpy. But there was a fellow who realized that if there's this stuff that expands and it's not in its ground state, occasionally it will decay to its ground state. And as it decays, you get this bubble, and as these bubbles grow, if you have a universe inside one of those bubbles, you get a universe that looks like ours. But it's just the way a boiling pot doesn't have one bubble, it has lots of bubbles. This inflation produces lots of bubbles. And the fascinating feature about inflation is that once it starts, it goes forever. There's no reason why it's going to stop, at least not according to our best understanding at this point. And so if it goes on forever, maybe it has always been going on forever. And I talked about the Hawking-Penrose singularity theorems. There's actually, for that theorem to hold, there needs to be 4 conditions. 1, general relativity's got to be true. 2, there's got to be energy of a certain amount of energy. Energy has to behave a certain way. And there's another kind of obscure one about closed time-like curves. Inflation has energy that doesn't behave that way. So you can't say, well, the Hawking-Penrose singularity theorems say that there's still got to be a beginning because inflation doesn't abide by the conditions which the Hawking-Penrose theorem, the singularity theorem, needs to work. And so this is a way of getting around the beginning that maybe the universe has, or getting around this idea for a beginning that perhaps it's existed forever. So does the multiverse actually avoid a beginning though? Well, it's interesting, if you go look at Arvind Bordig, Alan Guth, and Alexander Vilenkin, 3 people who are very prominent in developing inflationary cosmology, what they argue, and it's an interesting argument that if you want to know a little bit more of the details, I don't know whether you got a copy of my book, but I describe it a little bit more in one of the chapters. They basically come up with this: inflationary spacetimes are incomplete in past directions. And without going into all the details, what that means is that if you take an inflationary spacetime, which is how you get this multiverse, and you just trace it back in time, eventually you run into a boundary where you can't describe things anymore, that there's a boundary, or another way of saying, that's a reasonable way of saying there's a beginning to things again. So even in inflationary models, you end up with a beginning. So why I give all that is now we're talking about quantum gravity, and does that get around a beginning? And what do we even mean when we're talking about quantum gravity? So here's a little bit of the background of what we're talking about there. So if we look today, we actually measure, or we can describe our universe using 4 quote-unquote fundamental forces. There's the gravitational force, which we're all intimately acquainted with. The electromagnetic force, which whether you know it or not, you're also intimately acquainted with that, because that's why I don't fall through the floor, because the electrons in my shoes push back against the electrons in the carpet, which are pushing against the electrons in the wood. And so this is all the electromagnetic force. And you see me because the photons from the light are bouncing and getting absorbed off my body. It's all electromagnetic stuff. So we're intimately acquainted with the electromagnetic and the gravitational force. But there are these 2 other forces that determine how nucleons inside the nucleus interact with one another, and kind of this other weak nuclear force. And I say that weird because these all kind of are easy to describe in terms of what they do. This one's a little bit more complicated. It discovers why things decay and a whole lot of other stuff. We know it's there, but it's a little harder to get a handle on and describe. So we look at these and we say, hey, there are 4 different forces here, but you go back, actually while I was in college in the 1980s, 1970s, people realized that, wait a second, what we thought of this electromagnetic force and this weak nuclear force as being 2 distinct forces, it turns out that when the universe is in a higher energy state, when it's hotter, that they're actually identical. They're indistinguishable, and we talk about this electroweak force. And there are people who developed the theory related to that, and there are a couple of Nobel Prizes awarded for that. There were people who did some experimental work to detect some particles that are associated with that, a couple of Nobel Prizes awarded for that. And then just recently, Peter Higgs was awarded the Nobel Prize for the discovery of the Higgs boson that happened within the last decade or so. And so that's all related to this idea that these forces that we think are disparate can be unified into a common theoretical framework. And so since this works so glowingly well, the idea is perhaps these other forces are all unified into a common framework. And so you've got this grand unified theory which incorporates the strong nuclear force, and ultimately you get the gravitational force pulled in there, and you get this quantum gravity. Why that's all important is because when you look at general relativity and the singularity theorems developed by Hawking, they're based just on our understanding of gravity, which is a classical understanding of gravity. Even if you look at the inflationary models and the work by Bourdais, Guth, and Vilenkin, it's still a classical description of things. But yet our universe is fundamentally a quantum universe. And so if we really want to answer this question, we need this quantum theory of gravity out there. And we don't have that. We're trying to understand what it is. The difficulty is to be able to actually get experiments that do that are well beyond what our capacities to generate those sorts of energies. And so it's difficult to actually know what this quantum gravity is, but people will go and say, hey, wait a second, here's one way of looking at quantum gravity. And when you do that, what you get are a number of quantum gravity models where there's no beginning. It could, one of the models is, the universe has been contracting from time eternal in the past. It goes through this bounce, and now we're in the just after the bounce phase. Or you've got these cyclic models where it goes up and it gets smaller, goes up and gets smaller. Or it goes up and then it spawns a new universe. So there's just multiple ways where you have these quantum gravity models where even though it looks like our universe has a beginning, it doesn't. And so that's what this fellow was asking. And the question was, do these quantum gravity models get rid of the beginning? And the hard part about all of this is that we don't know which quantum gravity model is correct. Because I can give you quantum gravity models that don't have a beginning. I can give you quantum gravity models that do have a beginning. And so we don't have an answer to it. But even in the midst of that, as I was thinking about it, what I realized is this. I'm actually still pretty confident the universe has a beginning, and this is why. And it's not so much based on what we know today, it's why we know what we know today. So, when Einstein proposed his theory of general relativity, things looked more dynamic. One of the ways of getting a dynamic universe was to have one where it would expand out to a certain point, it would stop, it would contract, it would come back, squeeze down to a small point, rebound and expand out, and it would just oscillate back and forth. This is effectively a multiverse model, even back in the 1930s. We got one universe, two universe, three universe. So it's a multiverse model, and if you watch this too long, you get a little queasy, so we're going to move on to the next one. That was one way of looking at it. There was another model proposed not too long after that, especially after Hubble found that the universe was expanding, where the universe is expanding, but scientists hypothesized that maybe new matter is continually being created because in an expanding universe, everything is spreading out and getting more and more or less and less dense. And so what the idea was, perhaps there's new matter being created. So even though the universe is expanding, it basically looks the same at all time, because as it expands, new matter is created in the voids. And so over time, it just looks the same at all the time. And people were able to go and say, all right, well, if it's this oscillating universe, there's this interesting thermodynamic effect that as it expands, you use up energy, so some of the usable energy disappears, and so when it collapses back down, the next time it expands, there's less usable energy, and as it expands, it's going to grow larger the next time. And then it's going to grow larger than that, and I should have started smaller because that's as far as my arms go. But if you look and say, okay, so it expands and it gets larger and then larger, and you can still kind of extrapolate back, and you end up back to a beginning where it had to start. And so even this oscillating universe doesn't get around to beginning. The steady state model, it has predictions about what we should see in the universe. And so astronomers were able to go out and look and say, what the prediction is basically whether you look near or far away, the universe ought to look the same at all times. And you go out and look through your telescopes, and it just clearly doesn't look that way. So the steady state model didn't work as well. And so if you kind of look at the history of what's happened over the 1900s, we start back here at the start of the 1900s. The universe was eternal. It was static and unchanging. There was no beginning to things. Laws of physics varied. Einstein comes in and says, all right, general relativity, universe ought to be dynamic. Space and time are not fundamental. They actually have a beginning to them, it looks like. And the first thought that came up was, okay, maybe we've got an oscillating universe. So now you've got a universe governed by general relativity, but it doesn't have a beginning. But there were thermodynamic considerations that says, no, even this oscillating universe model has a beginning to it. So maybe if you got an expanding universe, and you say, all right, well, maybe you got the steady state universe. So you measure the expansion that says, all right, general relativity is right. It looks like there's a beginning. You come back and say, okay, no, it's a steady state model. It's expanding, yes, but it doesn't have a beginning. Well, that was the discovery of the cosmic microwave background radiation, was really kind of the nail in the coffin to the steady state model, because it just can't explain the cosmic microwave background radiation. And then further, you've got the singularity theorems developed by Hawking and Penrose that say, really in very generic terms, that if general relativity is correct and there's a certain amount of energy, which we're both very confident of those two things, as you run backwards in time, you eventually run into a boundary where space and time cease to exist, or at the very least, our laws of physics break down, and that's a beginning. But then you've got inflation comes along, and it says, wait a second, these singularity theorems, the way inflation works, these singularity theorems no longer apply, and the way inflation works, once it starts, it goes on forever. Maybe it's gone on forever into the past, and you get this multiverse, which is really cool, and it's far bigger, and it really don't need a beginning, except that it seems like there's another set of singularity theorems that say, even this inflationary multiverse still has a beginning in the past. And so now we come along and say, what about quantum gravity? Isn't that going to get rid of the beginning? And that's really the big question. Except as I look at this history, it's like we think the universe is eternal. We make scientific advance and it says, oh, no, this really points to a beginning. They say, all right, well, given this new discovery, here's how you have an eternal universe that doesn't have a beginning. And then we do some more work and say, no, that doesn't work. No, maybe this is a way we can not have a beginning. And then we go measure what's in the universe, and it's like, no, that isn't a good description. And so we come back to a beginning. And then we find this evidence that, no, there really is a beginning. It's like, no, well, maybe not. Maybe not. There's because of this model over here. And the universe just seems to keep pushing us back to this notion that it began to exist. Now, is this proof that the universe has a beginning? Absolutely not. But it does mean, at the very least, it means this, that when I say there's good scientific evidence for the universe having a beginning, there is an abundance of scientific evidence pointing towards there's a beginning. If I want to say, hey, I think the universe has a beginning and that aligns with what Scripture has to say, I'm standing on good scientific ground to make that correlation. And I think it's a reasonable extrapolation to say, if you want to say, okay, you know what, you're going to claim that the universe doesn't have a beginning, you've got to recognize that there's this history of, no, the universe doesn't have a beginning and the universe keeps pushing us back. And so rather than just saying, well, here, I've got an idea, or I've got a proposal, or I've got a model where the universe doesn't have a beginning, I'm reasonable to say I'm skeptical until you show me that that actually is what's going on. And so I'd love to get up here and say, yes, I've proven the beginning to you. That's just not the case. In fact, given my theological consideration, I don't know that we're ever going to have that sort of proof. We've got an abundance of evidence pointing towards it, but it just seems like God always gives us enough evidence to believe what he says, but never proves it to us. There's always a reasonable way to say that's not the case. So, did the universe begin? Well, the 20th and 21st centuries are littered with models that avoided a beginning, only to have the universe inevitably push us back to the idea that the universe began to exist. So I'm going to let John come back up just for a brief period here. I think we're going to have some Q&A after that.
Judeo-Christian belief, isn't that a multiverse model? You believe in heaven, we believe in hell, we believe in this universe, we believe that they don't interact or connect with each other. I could be in a spaceship and go to the four corners of this universe and never find heaven. How would you respond to it?
So that's an entirely different talk, where I got who's afraid of the multiverse just for that. No, I think you're right. When you look at Scripture, it describes this created realm. There's also the spiritual realm, which granted there's one that's physical and one that's not. But even just in that, there's this physical realm, and then there's the new heavens and new earth, which at least by some measure have different laws of physics than what we see today. And I use laws of physics in quote, which ultimately those are just related to how God is sustaining creation. So yeah, when I look at Scripture, I find that this universe is not all there is. There's more to it than that. And so that was ultimately what helped me realize that the multiverse itself is not antagonistic towards Christianity, because Christianity describes something that I would call a multiverse. So.
Okay. Richard? Anybody else raise your hand? You'll be next.
Okay. I don't think it's on.
Is the red button on?
How do you turn it on?
Oh, yeah, there's a button on the bottom.
Oh, okay.
There we go.
Okay, so you didn't use the word entropy anywhere in your discussion, and from my naive understanding of entropy, it's a measure of disorder, and entropy is always increasing, which means disorder is always increasing. So if that is some physical thing that's true, if disorder is always increasing, that means if you roll back time, there was a point in time where it had to start, because something that's always increasing has to have some start. So what is the relationship of this entropy law of thermodynamics to what we're talking about here today?
So it's a really good question, and I will just say straight off the bat that my knowledge of thermodynamics is small enough that I'm not going to give you probably an adequate answer for what you're asking, except to say this. What we do know is that our universe, our observable universe, what we measure in there, started off in an incredibly low entropy state. And whatever model we have out there has to be able to explain that. And so when you're in these quantum gravity models, effectively what happens is as they, so let's take the one where it's from eternity past, it's been collapsing. As it collapses, it eventually runs into this place where the quantum gravity, it's kind of like a sponge. You can squeeze a sponge so much and it effectively wipes out all the history, and you get down to that fundamental state, and then it rebounds from that. And so that model has a mechanism for taking what would be all of the higher entropy, squeezing it into that incredibly small entropy, and then producing the conditions that lead to our universe. The cyclical models have that same sort of thing. There are models where our universe just expands and space everything gets so spread out and so sparse that effectively you reset the entropy to zero, and then the Big Bang kind of happens again. And so those are the ways that people recognize you've got to deal with the entropy, and so there are mechanisms they have for dealing with the entropy that reset so that whatever else has been going on, there's conditions that reset the entropy to the very low value that's seen at the start of our universe.
trying to think why, ask why do, I think it's good for any level, like, I didn't know 9/10 of what you said before you started, but I could still see in the Bible it says in the beginning, so there was a beginning, so that's good enough for anybody that hasn't watched your talk. But I'm trying to think of other, maybe, it hit me, maybe another reason that we want to have a beginning is not just because it says in the Bible, but, the other religions that say that, the New Agers that say that we are God and the universe is God. Is it, we want to have a beginning and the universe is, like he said, entropy is kind of fading away. So if God and the New Agers are right, if God and we are God and we're all God, this God is falling apart and it'll be nothing soon. So what is the main reason you would say that Christians want to have a beginning? Is it to separate God from his universe, or, he's unchanging? What would you say?
So what I would say, and this is that I am convinced of the idea that what is true is the thing that corresponds to reality. And so we can go measure how the universe works, how it behaves at some level. I don't think we can't get all the knowledge, but there's certain things we can do. And so what I'm interested in is what is the truth of how things work. And so why I think the beginning is important is largely because that's what Scripture reveals of how things, that's what Scripture reveals as the reality that I have to measure things against. And so since the Bible talks about a beginning, there's two reasons, I think, well, there's at least one theological reason why that is important, is because God is the one eternal that just exists. And a fascinating exercise that I try and do every now and again that just kind of boggles my mind when I think about it. It's like, I had a beginning. My beginning was a little over 50 years ago. I can go back and think what that beginning might have looked like, what it looked like. Well, so I got parents and where we were living, and so there's a house and there's a city and there's my parents, and so what happened before their beginnings and what happened before their beginnings, and you get back and eventually, okay, there's no earth, and what would that look like? No sun, and there's still stuff in the universe, and then, I can keep running back, and then eventually you get back, okay, there's a beginning to all the physical realm, and you get past everything that's created, and you end up with God. And it's like, it's kind of, I am so tied to thinking in terms of physical that to realize that there's just this, I'm now interacting with a being that has no beginning, that has no, all the stuff that I think is important and fundamental don't apply. And so I think there's a theological importance to it. And a beginning establishes that there's something outside that caused it to begin. And so there's neat philosophical and theological reasons. But ultimately what I think the prime apologetic value is, at least when we're talking with scientific people, or scientific-minded folks, is that the Bible talks about there being a beginning, or things being, at the very minimum, dependent on God. That they're not, that God is the uncontingent being and everything else is contingent upon him. And so that has scientific consequences that we can go out and interact with. And so that provides a utility to go and say, hey, the Bible describes what we see of this world. That gives us confidence that you may not want the Bible to be true. You may not think the Bible has things credible, but it aligns with what we know, what we can measure over here. That gives us confidence to go in and look at it and say, what does it have to say? So I don't know, whether Eastern religions need a beginning to make things so that, I'll let them deal with their worldview problems. I'll just stick with mine. It's got enough for me to think about. But really, I think the fundamental issue is you can't, two uncreated things don't go well together. And so if the universe is uncreated, it's eternal, that is a theological problem. And I think more pressingly, hate that when I draw a blank on a word. What does it mean when it's like, more, not compelling. the more immediate concern that allows me to deal with this issue, not the big issues, is that the Bible talks about a beginning, and scientifically we can go talk about and ask, say, does that actually be there? Because if we find that correspondence between what Scripture says and what creation says, that gives us a good evidence that we've actually gotten to the truth.
I'm old enough to remember all the excitement around Ferguson's unified field theory at the time. So what is a good apologetic way to explain to people that our understanding of science, physics, is a constantly changing model and only as good as our current understanding, and that they are still just theories?
The best one is the one that makes the person you're talking to and think and say, oh, now I got a better picture. What that is, I don't know. The way I would describe it is this, is there are two errors to think, or there's at least one error to think in that. And this is one that Christians tend to be more common with, is, well, we can't trust science because it's always changing. Well, yes, science is always changing in that we thought Newton was right, and now we think Einstein's right. And the misconception is that we thought Newton was right, well, but we know he's wrong, and now Einstein's right. That's not really the case, because it took me a fair ways through my undergraduate physics to realize that, yes, Newton's wrong and Einstein's more right, but we act like Newton's right all the time because it works for so much. And the key point there is that Newton's way of looking at things works for a whole lot of stuff. Einstein just comes and says, you know what, I can explain all of that and more. And if you think about it, that's really the way we live our lives. I mean, when I was 10, I thought certain things, and there were things that I knew how to do. And then as I got older, I realized, oh, not only can I do that, I can also do, and I'll give you a real practical example where we do it, is that we tell our elementary school students, you can't divide by 0. And if we do it right, you don't say it's impossible to divide by 0. You tell them you can't divide by 0 because you don't know how to divide by 0. And eventually you get up into college or high school and you take calculus and you realize, oh, if you're careful, you can divide by 0. And so it's not that if you say it here, you can be wrong. But if you say it here, you say, here, I'm providing you a framework that fits within what you know, but recognize there's a bigger picture out there. And so that's the way I kind of see with science. It's like we've got a piece of the picture here, and scientists are always looking and say, can we expand our understanding of the picture? And that's really what's driving us towards this quantum gravity model. We could say, all right, science knows this, but science knows that we don't have that final theory yet because we don't have a quantum theory of gravity that works. That a single theory of gravity that we can distinguish and say, these ways of looking at it wrong, this one's right. And so we're just always going to be increasing our knowledge. And as Christians, I would argue that that's what we're going to be doing with God for eternity. The stuff that I've learned, I may have learned some wrong things, but basically I've got a lot of the picture in place, but I'm going to be learning about God forever in eternity, and I'm never going to get tired of that. So this idea that science is always changing, yes, but that's because it's always getting more and more knowledge, and that's a good thing. That's the way God's designed us.
Jeff, thank you, number one.
Oh, there we are, okay.
And thank you for what you do. I'm a lawyer, and so this is admittedly a question grounded in ignorance.
Wait, are you saying all lawyers are ignorant? Because my daughter would be offended at that, and I was going to defend her there. So.
You started the talk by talking about the speed of light and the distance of objects and the time it takes for signal. And somewhere in there, I think you may have said that the speed of light is constant and static and unchanging and been the same forever. Do we know that? Do we know that the speed of light has never changed over time?
So, yes and no. And you get a lot of those answers from me if you ask me too many questions.
How do you
So,
sound like a lawyer?
that's why I was going to get offended if you, no. So the reason why I say this is that There's strong evidence that the speed of light is constant. In fact, part of what Einstein was talking about with the laws of physics always being the same is that one of the things that it plays into there is that everybody always sees the same speed of light. And so for having light, or the speed of light change as you move throughout the universe, that would mean general relativity is incorrect. And so to the extent we've validated general relativity, that gives us confidence that the speed of light is constant. There are some observational things that point towards that. Among a whole wealth of them is that I can go into the lab and measure spectral lines from certain atoms. And in order to understand and properly calculate all those, there's this thing I need called the fine structure constant. And it's related to the speed of light, the charge on an electron, and I believe the mass of an electron. And so it's just related to those three quantities, all of which are fundamental quantities, or constants, if you will. I can measure those in the lab. I can go look out at distant objects in the universe and measure that same fine structure constant. And to our best measurements, within 1 part in 100,000, they're identical, whether I'm looking in the Andromeda galaxy, whether I'm looking at stars in our galaxy, or whether I'm looking at distant galaxies most of the way across the universe. So there's strong observational evidence that the speed of light is the same everywhere. Now, given all of what I just said, as people are looking at these quantum gravity models and what's going on in the early universe, some of those have the speed of light change in there. And it's a little different flavor than being problematic with Einstein's general theory, or this notion that the laws of physics are constant everywhere. So the yes part is all the evidence we have says that the speed of light is the constant. When we're trying to understand the earliest moments of the universe, it may be there's some variability in these things that we think are constant at this point. Does that answer your question? Good.
Mark
Oh, sorry, yeah, here.
I was going to ask that same thing, because there's a Netflix cosmological about the guys in the 90s that invented I think the universe expands and it gets so big that it blows up again, and it's a Netflix on there. Okay, so I still wanted to keep going with that just a little bit.
Sure.
So I thought there were some theories about the speed of light around the event horizon and the black hole changing, because we don't know whether it's a particle or a wave. And so if gravity is that great at the event horizon, then the speed of light changes. And there's some other theories about at the very edge, okay, you're saying, but we still got to have speed of light constant, because if the speed of light speed changes, then we can't say it's this far away, right? So, I mean, if I say that out there it's going 200,000 miles per second or 500,000 miles per second, then that changes the fact that I'm saying it's this far away.
So
Light has to be constant.
well, I mean, there's a little bit. I think that this is one of those. You got to be careful, because there's things. Part of studying a discipline is learning. You kind of apprenticed into it, and there are things you learn where it works well and where we know we're doing it. So you talk about out on the event horizon. Well, that's where you need that quantum theory of gravity again. And so that's really, there are places where to answer what's going on with the speed of light, we need a quantum theory of gravity, and we don't have that yet, and so it makes it hard to talk about it. Again, what I will say is this: every place where we've looked in the universe, we see that the speed of light out there has the same value as what we can have here, to the extent we can measure it. And you just have to realize that even though we talk about these four fundamental forces, which we now know behave differently and are a low energy manifestation of a fundamental force, or a fundamental law, if you will. So sometimes the language gets confusing, but I'm not explaining this well. There's the when physicists talk about the laws of physics being constant, it doesn't mean they're static. It means they behave a certain way. And so even within our discussion of these fundamental forces, the fact that as they go to higher energies, they look a little different, that doesn't mean they're not laws of physics. So they're still understandable. They behave exactly the way the mathematics and our understanding of them say. And so that kind of, what that means is that sometimes we'll look in there and say, does the speed of light change? Well, it may be in these quantum gravity models we get into a realm where it's a different value than what we see, but it's what we would expect given what the model says. And so I just want to get away from that notion that just because things might take a different value doesn't mean they're not constant.
Right.
And that sounds really weird if you're not a physicist. So.
Sure, that makes sense. I mean, at the moment of time, or whatever, at the beginning, or at the event horizon, it could be different, but that's still a constant. It should be different.
It's behaving the way our theory says it should.
Yeah, right, okay.
Right here?
Yes.
If we believe that in the beginning God created, and at a certain day, he said, let there be light, that was instantaneous, and the light just was.
And so the question
Back
is,
to a million years ago, right?
what's your question? I'm not entirely sure what the question is.
The light that God created became visible immediately, right?
So that's there's at least some room for interpretation in this sense, that when you go look at Genesis 1, in the beginning God created the heavens and the earth. That word for created, bara, is kind of, only God can do something new bringing into existence when we're dealing with Genesis 1. We tend to look at the rest of the creation account in Genesis 1 as God created this, and God created this, and God created this, and God created this. And it's not correct, because God created the universe, God created a few life forms, and God created humanity. Everything else in there is God said, let there be, let there appear, God made. And all of those other terms have this connotation that process is involved. And so God said, let there be light. He didn't create the light. He said, let there be light. Now, if I look at what Genesis says, in the beginning God created the heavens and the earth, the universe, sun, moon, stars, and all that sort of stuff, and the earth was formless and void, darkness was on the surface of the deep, and the Spirit of God was hovering over the surface of the waters. So where are we witnessing the account that comes after that? Well, the Spirit is moving over the surface of the waters. So you've got the earth covered in waters. It's dark on the surface of the earth, but yet God's created the universe. Sun, moon, stars, and all that's out there. So how can all of that stuff be out there, and yet it's dark on the surface of the earth? Well, one of the best ways is have it just be covered in something that is preventing the light from penetrating. So when God said, or on the first day, and God said, let there be light, that isn't God created light, that is God let the light get to where it was witnessed on the surface of the earth. God separated the waters above from the waters below. Again, that's a let there be. There's some sort of process involved. And God doesn't articulate what the process is, but he does tell us there is something going on there. This isn't just, boom, it's this way. So, and why I say that is because if we say, well, the light had to be created instantaneously, the land had to be created instantaneously, the sun, moon, and stars had to be, or the greater light and the lesser light had to be created instantaneously, we undermine something that is very important, is that God created the universe, brought something new into existence. God created certain animals. God created humanity, brought something new into existence. But God created and made humans. So there's a physical part that God had made or created earlier and made into humans, but then God created us in his image, that he put into us something new that never existed before. And so if we confuse and say God created all this stuff when there are processes involved, we undermine the fact that God created us with something entirely new that didn't exist throughout the rest of the creation. And so that's why I made a big point about that. So I think my contention is, by the time you get to the start of day one, the universe is probably close to 10 billion years old. There's a whole lot of stars out there. The sun's already out there. But when you're on the surface of the earth, it's dark, it's formless and void, it's inhospitable to life, and it's covered in water, which interestingly, from our understanding of planetary formation, that's exactly what you would expect an early planet like Earth to look like. So once again, we find this biblical description and the scientific description aligning there.
To follow up on that real quick, so just to emphasize the point you're making, that in that chapter there are different Hebrew verbs that are being used. That's the point that you're making.
Yes.
There's a Hebrew verb that's created. There's another one that's translated made. It is a completely different Hebrew verb that has a different meaning.
And we, in English, we tend to think, oh, that's not a big deal. But in Hebrew, go look in your Strong's Concordance. There are 8,000 Hebrew words in all of the Old Testament. 5,000 of those are proper names. So in the entirety of the Old Testament, there are 3,000 words used to communicate everything that's there. English language has something on the order of 2 million. So when we use a different word, that's clearly we're trying to distinguish. But when Hebrew uses a different word, clearly there's something else going on, because the same word is distinguished by the context and how it's used. So that really is an important, Jeff Zweerink, the devout Hebrew scholar here, even I know that there's something important going on there. So
If I can just re-articulate her question real quick,
okay.
One of the things that she might be appealing to is this belief that you hear sometimes from people who object to the millions and billions of years, is that God could have created the universe in its state with light en route, okay, so it appears like it's old, but it wasn't. God just made the universe in its current state. It's been expanding maybe a little bit. The light was in place. You see any troubles or issues with that?
Yeah, and the first thing I would say is, yeah, God, as long as it's consistent with his character, God could do anything. What he's charged us to do is to figure out what he did. You know, so he's revealed enough that we can investigate, but then he's charged us to go out and study. In fact, the command given to Adam and Eve is to be fruitful and multiply and fill the earth and rule over it and subdue it. Well, how do you rule over and subdue something you don't understand how it works? So he's told us, go understand. Now, you may say, man, that doesn't apply to the stars because we don't have any control there, but I still think there's that mandate to go out and understand creation. And so, if everything was created mature, the question I would have about that is, did God create Adam and Eve mature? So physically they may have been mature. Did they have memories of their childhood? I don't think so. But if God created the universe mature, he created it with memories of events that never happened. For example, my graduate research in 1990, we were finding these galaxies that gave off gamma rays. And in May of 1995, the telescope we were using detected an outburst or a flare from one of these galaxies where the gamma ray intensity increased by a very large amount and decreased over the span of about half an hour, which is remarkable considering what we're looking at. Now, this galaxy is 400 million light years away from us. So if the light was created in transit so that we could see it here, there's this signature of an event that is in that beam of light that we detected in 1995, but the signature of that event, because if you run it back and say, when did that event happen? It happened never, because God created it mature. So God created the universe with memories of events that never happened. That's my big problem with creating it mature. And I don't think he created Adam and Eve with memories of their childhood, but yet, and for that same reason, I don't think he created the universe with memories of events that never happened either.
You
So,
create them with memories of a childhood that never existed.
right.
Amen.
Well, this sort of question somewhat bounces off of that. First of all, what you were just saying, was that sort of the concept of if a tree falls in the forest and nobody is there to hear it, there's no sound or there is sound? Is that somewhat of what you were saying there about biblical creation, universal existence?
So, you know, the tree falling in the woods, if no one's there to hear it, does it make a sound? That's asking the question, is sound dependent on conscious perception, or is it just the waves moving through? And I would say the tree falls on the ground, it creates the reverberations, the compression waves in the air, and so in that sense the sound is there whether there's anything to detect it or not. But what I'm making is, or what I'm talking about here is a different question, because it could have been that whoa. Sending that one back. All right. So I can guarantee that there are numerous events where things have happened and the light waves have passed by us and we've never looked at them because we didn't have the technology. But the question I'm asking is that when you see in a beam of light a fluctuation, so if the lights get darker, lighter, dark in here, it's because a switch is flipped or a short circuit happened. It's a signature of a physical event that happened. And so the fact that we're seeing signatures that require an event to produce, or they have to be just created out of thin air, I don't think God just created things out of thin air that are the same. We look at things and we say, oh, because of this happened. I see this, that means this event happened. We look at this and we say, oh, we see this, that means this event happened. But if the beams were created in transit, that event never happened. It seems like that's deceptive. I don't see how you get around that being deceptive. So it's a little different than just whether we're hearing it or not. But it would be God putting a record of an event that never happened. And I just don't see that being consistent with the character of God. Yes?
Yes, hi, Dr. Zweerink. I remember seeing a number of Ross videos on the space-time theorems.
Okay.
And I think what Hawking's and Penrose is like one of the early ones, but then
Right.
there were some other ones that added in quantum effects and other things. And I remember Dr. Ross arguing, well, that says that there's definitely a beginning. I mean, it's a theorem.
Mm-hmm.
But yet these quantum gravity type things, I mean, science develops over time. And that's one thing I was struck by your talk.
Right.
So are those theorems not as valid, or is this something that's like it's coming out of the initial part of the Big Bang where the energy state is very high and there could be other...
So what I would say, how I would answer that is this, is that every theorem has a set of conditions that predicate it. So for the singularity theorems that Hawking and Penrose developed, you go read the paper and they say, if general relativity is true, if there's this kind of energy, if energy behaves a certain way, if. So as long as those four conditions hold, the singularity theorem holds. If one of those conditions doesn't hold, the singularity theorem no longer applies. When we're talking about the beginning of the universe, until we have a quantum gravity theory, our theorems will inevitably be incomplete. And so the question is, given the ifs, are any of those violated? And so almost every time there's been a singularity theorem, somebody comes along and says, all right, well, here's a way of doing it that this if is violated, and so this theorem no longer applies. And I don't think that process is ever really going to stop. There's the here's what the science says, and now here's Jeff Zweerink's kind of personal opinion. Take it or leave it. When this fellow came and said, well, what about this? Honestly, my thought wasn't, wow, maybe I'm wrong. I always thought, okay, well, I need to go think more deeply about this. But the reality of it was, I thought, okay, Christianity has a good answer. How would I respond to that? And so I developed a response. You can tell, I think Christianity's correct. I think the Bible's got a good description. And so here's my argument why it is. Now, my skeptic friend, he didn't just say, well, oh, yeah, you're right. He said, well, okay, that's a good argument. How would I respond to that? And so he's going to come back with a different argument, which the last time I heard, his argument wasn't sufficient to cause me to doubt my argument at this point. And so he's going to come back. And then I'm going to say, well, okay, that's, to the extent he's got a good argument, I'm going to sit there and weigh, okay, well, where is that? And, if I'm honest, at some point I'm going to say, okay, does this really invalidate Christianity? But in order to invalidate Christianity, there's a whole lot of other things you have to answer in my life. Like, how did how do I account for the fact that there are specific instances where God's answered my prayers? How do I account for the fact that Christianity really does the best explanation of everything? So there's a whole lot more to that. And so some of this is, again, this is Jeff Zweerink's personal opinion here. Take it or leave it as you want. I don't know that game of here's an argument, here's a counter argument, I don't know that it's ever going to stop.
People are always trying to develop models to describe more and more.
Right, yeah. I'm just convinced that the more we do that, the more it's going to look like Christianity's true.
Okay, good.
Yes, LD.
Good morning. Thanks again so much, Dr. Zweerink, for coming and blessing us with your knowledge and your insights. So we appreciate that. Simple question, this not being my paradigm. Just intuitively, when I think of expansion, inflationary concepts within the universe, we talk about inflation. First off, does an expansion occur at some point faster than the speed of light?
That's what I was wondering.
So the short answer to that is almost inevitably yes.
Okay.
That's going on in our universe, not in our observable universe, but just outside the bounds of our observable universe. Things are going to be moving away from us faster than the speed of light. In inflation, that was just magnified because the expansion rate was much greater than it is today.
Okay, so spinning off of that, just again, basic conceptually to me, there should be a point in time where an observable light matter, a star, a galaxy, goes beyond our that is, we could see it and then we couldn't see it because it's expanded further away from us than we can observe. So if there is such a boundary, has that ever been observed or is that theoretical?
So,
Could you repeat his question?
so his question is, okay, so if things can expand away from us faster than the speed of light, then presumably there's a maximum distance something could be where we could see it, but things are going to be expanding across that boundary. And so things will be within our sight and then will disappear from sight. And so yes, people have thought about that, but it doesn't happen quite the way. It's not like I see a star, I see a star, I see a star, boom, it's gone. Because what's happening is the light is as the thing is propagating through space, space is expanding, and so effectively what happens is the light just gets infinitely redshifted. And so it's not like it's there, it's gone. It's that the light gets more and more and more and more red, and eventually it just gets beyond our ability to detect. And so people have thought about that, and it's just not nearly as cool as that one just went, which would be kind of cool, but it just doesn't work that way, so.
This is the penultimate question, next to the last.
That sounds like it ought to be better than ultimate. I know it's not, but it sounds like it ought to be.
That last question was great because I was just going to say I would never understand why 18 billion light years out we just wouldn't see it. That you'd be down to, first it goes red, then it goes microwaves, then it goes something we don't have a name for.
Oh, radio's
and
next.
Then you don't see it, and radio waves, and we don't see it. But just go back to this is a football. You said that they proved Einstein right in so many ways. So my dad had something called a storage ring, and he told this is where my knowledge ends, and it's like, what is a football for you? But it was like if you get an electron closer and closer to the speed of light going around, you pour energy into it with the radio frequency accelerator. The thing gets heavier and heavier. They can demonstrate it, and my impression was if you kept pouring energy into that electron, it would eventually, and it gains mass. Is that not correct? As you get closer to the speed of light, this electron.
It's a nice colloquial way to say it. It's a little bit more complicated. The more energy you pour in, the more energy you have to pour in to make it go. And so you can talk about that as though it's getting more massive. But yes, so.
I don't know. I thought you could keep pouring energy into that. I mean, don't we always take something to the ultimate ridiculous? If you kept pouring energy in it, wouldn't it weigh as much as the universe? You'd pour all the energy of the universe into that one electron, and it would weigh as much as the universe. So how could things be going outwards faster than the speed of light?
Because you're talking about two separate phenomena there. Because you cannot make something cannot travel through the universe or through space faster than the speed of light. And so that's what you're talking about with the electron. You're trying to make it go faster and faster and faster, and so you got to dump more and more energy to do that. That limit does not apply to how rapidly space can expand. So the reason why things out at the distant edge of the universe are traveling so fast away from us is that the amount of the space between us is expanding. So the difference in picture, imagine I've got a rubber sheet here where things are kind of sticky on it. There's a limit to how fast things can roll across the sheet, but I can stretch that thing far faster than that limit. That's what's going on with the universe.
Last question. So, one of the...
You get the first and the last question. This man is important right here.
So, there's a very common refrain, if God created the universe, then who created God? Okay, so this is a philosophical question, but I think it bears on the topic today.
Mm-hmm.
Wouldn't it be rational to say, no matter what your worldview, you ultimately have to believe in an eternal, uncaused cause of some kind? Whether that cause has a capital C like God, or whether it has a small c like some sort of universe-generating machine. Isn't that rational to say?
Yes, it is, and at least, I mean, so this fellow that I was interacting with when I wrote the book Escaping the Beginning, I had him be one of my reviewers, and so in one of my chapters in there, I talk about, okay, so if, because something had a beginning, something needs to not have a beginning. So because the universe, Statue of Liberty is where I start off with all that, if you want to know. It's kind of an interesting story, if you like David Copperfield and magic. But because something has a beginning, something has to be eternal and that ultimate cause. And so you're left with kind of, as I look at it, you're kind of left with three things. One is that God is the uncaused cause, or matter is the uncaused cause, and that's why, if the universe is eternal, then you could argue that you don't need God because the universe can serve as that eternal uncaused cause. Or a fairly common one today is that the laws of physics are the uncaused cause. So I know Stephen Hawking basically made a claim, and Lawrence Krauss makes a similar claim, that given the laws of physics, the universe will exist. So he's transferred the laws of physics, which throughout history have been descriptive of the way the universe behaves. He's changed them to a self-existent entity that now can cause things to happen. So you do need to end up with an uncaused cause. It's either God, it's either the creation, the physical realm, or it's the laws of physics. One of those three seem to be the common options today.
So for anyone to ask about your uncaused cause, who caused that, that's really a pretty silly question.
Say that again.
So
because different people like different uncaused causes.
Right. So when they say, well, if God created the universe, who created God? Well, if God is your uncaused cause, it stops there. It's a rational position. If they believe that the universe is eternal and that matter has always existed, sometimes Christians will say, well, who created the universe? Well, that's kind of a silly question because they believe that the universe is the uncaused cause. So.
No, you're right. It's not like the fact that I had a beginning means that something didn't have a beginning. The question is, where do you end up on that? And so the key thing about God, that the thing that gets missed in that question is that if the universe had a beginning, it needed a cause. If God had a beginning, he needed a cause. But the way Christians describe God by studying his revelation in Scripture and creation is that God didn't have a beginning, therefore he doesn't need a cause. That's the same logic they're applying to the universe didn't have, the physical realm didn't have a beginning, therefore it didn't need a cause. The laws of physics didn't have a beginning, therefore it didn't need a cause. What I like about God is that he's the uncaused cause that actually causes the laws of physics and the physical realm at the same time. So.
Amen.
So, well, thank you. Appreciated the time here and great questions.